Thank you all so much for being here. My name is Ian Sieb. I am with Denver Relief Consulting, one of the sponsors of today's symposium. Thank you very much. Please don't clap for me. Let's the real intelligence sits to my left. We're here for the final session of the day. It's a general session called Lighting and Energy Management Systems. So here today with me are three very well-versed professionals from the lighting industry. We have first, to my immediate left, is Brian Bennett. He is the founder and CEO of Thrive Agritech. He likes to, or we have decided collectively that he is the photon nerd amongst the four of us. Sitting in the middle is Shelley Peterson. She is the Vice President of Lighting Technologies for Urban Grow. And at the far end of the table is Bob Gunn. He is the founder of Synergy LLC. He's an energy geek and an Excel robot. So we're going to kick it off. Brian's going to start for us. We're going to speak a little bit about lighting. Shelley's going to give us some information about different technology options and laying out facilities. Bob's going to speak with us a lot about rebates and the opportunities that are afforded to those involved in cultivation and some significant cost savings that we think many cultivators and cannabis operators may not be aware of. And then we'll do a Q&A. So with that, Brian, go ahead, kick it off for us.
All right, thanks for that great intro. So in the 10 or 12 minutes I have to talk, I want to cover three main things. First, general grow light 101, what is a photon, why do you care? Then getting into tips and tricks for an efficient lighting design, and then a few thoughts on where I think that the future of sustainability in indoor cannabis, especially as it pertains to lighting, is concerned. So, when we talk about grow lighting, we're always talking about photons. That's what a plant cares about, photons. So a photon is this really wild thing. It's this incredibly small piece of light. It's so small that sometimes it's a wave and other times it's a particle. And for photosynthesis, it really acts like both a wave and a particle. When I think about a photon for photosynthesis, for growing plants, it's always about transferring energy. It's a packet of energy that when it hits a plant, it can do something. You can have H2O and CO2, hit it with a photon with the right properties, and you get photosynthesis. There's all different types of photons, from X-rays to gamma rays to radio waves. What we're concerned about, photosynthetically active photons. So those are photons 400 nanometers to 700 nanometers in wavelength. It happens to be, maybe a biologist or evolutionary biologist could tell us why, the exact same frequencies that people can see. So you often hear about the visible wavelengths, the blues to the greens to the reds. Exact same colors that people can see are the exact same colors a plant can see for growing. Kind of interesting, when you think about wavelengths, the wavelength of a far red photon is about the same size as a piece of bacteria. So the actual photon itself, incredibly small, but the wavelength, about the size of bacteria. Where compared to a radio wave, it might be 60 miles long. Still the same size photon, just a very long wavelength. And it's that size of the wavelength that really affects the energy it can carry, and then exactly why and how a plant can use it to grow. So, when we're talking about grow lighting in an indoor facility or a greenhouse facility, a photon is too small to talk about. You never think about single photons or thousands of photons or even millions of photons. You talk about moles of photons. In a mole, it's just a big number. It's 10 to the 23rd photons. So if someone says they have a mole of light, they just have 10 to the 23rd photons. And of course, it has to be more complicated than that. So sometimes a mole is just too big of a number. So we have to talk about micromoles. So a micromole is just 10 to the 17th photons. If you have a light that's emitting 1,000 micromoles, it's simply just 1,000 times 10 to the 17th photons. So it's just a way to put it into human scale, because a photon's just way too small. What you hear a lot, especially as it pertains to lighting, is PPF. That's photosynthetic photon flux. It's just simply the total number of photons the light is emitting. It doesn't matter in what direction the light is emitted or if it's hitting your plants. It's just the total amount of light that a light is emitting. We measure it in micromoles per second. What you really care about in a facility is ppfd. It's probably the most important characteristic as it pertains to lighting for an indoor grow facility. It's the number of photons that are hitting an area per second. So it's simply just micromoles per second per square meter. If you take that 1,000 micromole light, take all those photons, jam it into a 1 meter area, you have 1,000 micromoles per square meter ppfd. If you spread it out over 2 meters, you have 500 micromoles per second per square meter. So it's just a measure of how many photons are hitting your plant, but it's the single most important characteristic when you're talking about designing efficient lighting for an indoor built environment. We're talking about lighting and sustainability, so what you really care about is the efficiency of the light fixture. You have electricity coming in, it enters a light, it doesn't matter if it's a high pressure sodium light or an LED light. We convert the energy from electricity, from electrons into photons, and we want to do that as efficiently as possible. So the way we measure that is the total number of photons you create per input energy, so per joule. So as many photons as you can create, micromoles per joule. A higher number just simply means you can create more light with the same amount of input energy. So now that we know what these photons are and why we want to use them, how should we design an indoor environment? We talk about lighting design all the time for our everyday life, for rooms like this, for classrooms, for hospitals, for offices. We all can see a proper lighting design. We know when it's designed well and we're comfortable in that space. It's the exact same thing for plants. They know when it's designed well, when they're comfortable in that space and they're growing well. It's just we can't see it in the same way a plant can see it. So what we really care about from an efficient, sustainable perspective are photons hitting the plant. You can have the most efficient light source, but if it's shining on the wall or shining on the floor, shining on the aisles, it's wasted energy. It's not sustainable. And it's a little bit complicated because every light is different. You have a high pressure sodium light it's a point source. It emits a lot of photons from one distinct point. And then you want to spread that out over your plants. Compared to maybe a fluorescent light or an LED strip, it's still emitting a lot of photons, but from a totally different form factor. So it's challenging as a lighting designer to create a system by which the photons actually hit the plants. So what you should do as a grow facility manager or someone who's specifying lighting, work with the manufacturer to create a lighting model. Every lighting manufacturer has computer models that say exactly how many photons our lights are emitting in any given direction. And we can plug this into a computer environment and exactly map for your specific grow space exactly how many lights you need, how to space them out, how high to mount them, so that you're optimizing your space. No one would build an office building, no one would build a hallway or a hospital without a lighting design. You should not build your grow facility without a lighting design. Even if you have the best design out there, photons will miss your plants. Some of them will shine on the wall, some of them will shine on the floor, some of them will actually hit the leaf and bounce off. Paint your walls, paint your ceilings, paint your floors white. It sounds like it wouldn't make that big of a difference, but in just about every facility, it will increase the brightness on your canopy by at least 20%, sometimes much more. Those are free photons, that's free energy. You might as well paint your floors white because you're gonna paint them some color. And that's just simply gonna save you 20% of your lighting energy, maybe more. I said ppfd is the most important characteristic, but maybe uniformity is the same, it's just as important. What you want to avoid is having bright spots and dim spots on your plant canopy. It affects everything from how quickly a plant grows to how it uptakes nutrients to how the flower's development. It wastes a lot of energy. The plants, if you have a bright spot, like you can see in the picture, those plants grow much more quickly. But they're also hitting their saturation point. You're feeding it more energy than the plant can necessarily take. And then the plants in the dim spots, they're missing out on growth opportunity. They're not seeing enough light. So all said and done, you're wasting energy as compared to having a uniform plant canopy. We would recommend targeting plus or minus 5% uniformity. Plus or minus 10% is acceptable. The higher the uniformity, the better your plant growth will be and the better your sustainability will be. Again, this comes back to a lighting model. We can figure this out really easily in the CAD environment, and then it's easy to confirm once you install the lights by walking around with a photosensor and just confirming that the model, it agrees with the real world. Okay, so the future. Where do I think that efficiency is going to go? Personally, I'm quite excited about it. I think over the next 5 to 10 years, we are going to see a doubling in grow light efficiency. The theoretical maximum, as far as micromoles per joule, it's about 5. That's with a 100% efficient light source, you will get 5 micromoles per joule. Most LED engineers would agree that the practical maximum in the real world is about 4 micromoles per joule. And this is really exciting because over the next few years, we are going to see this. So every grow facility from a lighting perspective, twice as efficient as it is today, which means it needs less HVAC, it needs less electrons in general. If I were designing or putting together a business model for the growth environment, I would take into account the efficiency trends for LED. Data will also be a big deal. You hear a lot of buzz about this with artificial intelligence and machine learning. And that's partly because the amount of data points collected by both indoor and outdoor farms is skyrocketing. Billions of points collected every single day. My personal feeling, AI and machine learning will be really important in the mid to long term, but I would value human intelligence along with data in the near term. There's a lot we can do by collecting these data points and packaging them together, and a grower can take this data and really move the needle on efficiency, on how much light a plant needs, when it needs the light, what colors of light does it need. These are the type of things that we can look at now and really will impact the future as we get more connected sensors in the built environment. And lastly, demand response. I think we'll be talking about this more later, Bob, but this is something that I think is both the future and the present. It turns out utilities, they need to, we know this, they have to produce power every minute of every day, 365 days per year, but there's only a handful of days per year that are the trouble days. So maybe 5 days each year, usually in the summer where people are cranking up HVAC, where the utility struggles to provide enough energy to everybody. So what they do is they build all this extra capacity. They make sure that they invest in the infrastructure to be able to provide all of that energy. It ends up costing you every day of the year 25% or more of your bill just to provide energy on these few days. It's not even all day on those few days. It's usually just a few hours each day. So you're spending money year round to provide energy 40 hours a year. I think that the indoor cannabis industry has this unique opportunity to work with utilities in order to work to shave off some of this peak demand. Because we can reduce the canopy PPFD for maybe 2 hours a few times per year from 800 PPFD to 400 PPFD. It would be like a single cloudy day a few times a year. And that will solve a massive problem for grid management. Right now, people are investing in batteries, they're investing in all kinds of energy storage. I think that cannabis, being a really stable 365-day per year indoor production that consumes a lot of energy, has a great opportunity to sustainably work with the grid. Thank you.
Thank you, Brian. Up next, we're going to have Shelly from Urban Grow speaking with us. I do want to, for a minute, just pause to thank our sponsor of this session, BIOS Lighting. BIOS is an LED company that is based out of Florida that is really on the forefront of creating some new LED lighting technologies. And if you haven't spoken with Neil Yorio, who is here visiting from Florida, I would encourage you to do so. So thank you to BIOS for sponsoring this session. And with that, we'll give it up for Shelly.
Thanks. Hi, everybody. So I'm going to focus on how do we as an industry try to create something that is sustainable, and with the target on lighting, and how do we lay facilities out smarter and in a more efficient way with the existing technology that we have, while also looking at budgeting and costs for the different types of technology that are on the market. So the bigger picture right now is cannabis is not currently sustainable. As margins decrease, production costs will need to decrease as well. And when you have a big piece of the pie for every operating facility that's electricity costs, how do we start to bring that down, maximize square footage with the right types of technology? So how do we educate to make sure that people are making informed decisions and not just relying on technology that they think works and trying to understand why it works? So this was put out a few years ago and is a chart that's used a lot. And as you'll see, is lighting makes up about 1/3 of the energy in a commercial cannabis facility. And then most of the other costs associated with operating a facility are directly attributed to the lighting in that facility. So it's really important to understand which lighting you're putting in, why you're putting it in, and how to maximize it. So as more and more states are starting to turn to greenhouses, how do we light these correctly, adjust the lighting schedules to make sure that you're using electricity in the right places, and then most importantly, how do you target the right DLI? So Brian talked a little bit about what is a micromole, what is a mole. I'm going to go into it just a little bit more, and then how do we maximize the square footage of the light fixtures and also measure that light to make sure that we're not wasting it when we don't need it. So DLI is the accumulation of light. So a micromole is an instantaneous reading. So if you have a Lycor meter or you have a professional light meter, you're measuring the instantaneous reading, which is measured in micromoles. DLI in moles is the accumulation of that instantaneous reading over the photo period that it is. So in a greenhouse, you're receiving a lot of your light from the sun, and then how do you supplement it with an artificial light source? So here's a slide that shows a little bit about where cannabis is grown optimally. So cuttings and clones obviously need a lot less light than the flowering plant does. So most growers now are using their veg cycles for 18 hours a day. So cuttings need roughly 13 moles of light per photo period, up to 32 moles, and then you kick it into flower where it needs more moles. So over a 12-hour photo period, you're looking anywhere from 750 micromoles up to, on the pretty high end, 1,000 micromoles. And then that's converted back into moles. So somewhere between 30 and 45 moles is what most people are targeting. So if you look at this slide, this is how many moles of light per day are reaching each month. So if you look at Colorado here, you'll see in January and December, outside, they're only getting, that's my phone.
Should we answer it?
This has happened to me before, and it just happened again. Oh my God, sorry. So in Colorado, it's somewhere between 15 and 20 moles of light per day outside. So when you start to put structure over the top of that, glazing over the top of that, you cut that number back, and then you try to start targeting how much do we need to supplement. So in Colorado, I'll go back to here, in the flowering stage, if you have roughly 10 moles per day in the winter time, and you need to get to 35 moles, that means you need to supplement 25 moles of supplemental light in your greenhouse. So some efficiency tactics. Brian talked a little bit about sensors and where the industry is going. I completely agree. There is some sensor technology on the market right now that measures light really well. They're called weather stations. You can put them in your greenhouse to make sure you're targeting those light levels. As sensor technology continues to develop, we're going to be able to capture that data With LED lighting, we'll be able to turn lights on and off depending on if there's a cloud overhead to make sure that you're targeting that right amount of light per day. So LED is a lot easier to control than HPS. With HPS, you have to wait for the fixture to cool down, turn it back on. It's a lot harder technology to manipulate than is LED. LED you can dim, you can lay the facility out in more ways. Just as technology evolves, it's going to be a lot easier to start to manipulate and control that light. So as you start looking at the different light fixtures that they are, getting professional light plans from manufacturers, most manufacturers have the capability to do it. Making sure you're validating what those light plans are. Here's a hybrid light plan that we did that shows what the total wattage is for this example room that we did. So roughly 82,000 watts it would take to reach around 800 micromoles. So if you compare that and run an ROI analysis, you would need approximately 85 HPS fixtures to reach this same light level. So with a hybrid lighting design, you would save roughly 10% in energy. Now, if you used an all LED light plan to do that, you would save roughly 35 to 40% in energy. And that's with LEDs that are the most efficient on the market currently. Something that is really important to talk about is with LEDs, not all LEDs are created equal. So I'm going to skip ahead to this one, I'll come back. This slide shows if you have an LED fixture that's roughly 1.5 micromoles a watt, which they do exist, and you have a fixture that puts out 640 watts, the light output of that fixture at the surface would give you 960 micromoles. Compare that with a double-ended HPS fixture that would be 1.8 micromoles a watt and you would have 1881 micromoles. So you would have just cut your light level by roughly 50%. So efficiency of those fixtures, how many micromoles per watt is coming out of the light? Now, if you have an LED that is the same efficiency as a double-ended HPS, but 40% less watts, you're still going to cut your light level by 40%. So the only way to swap out LED, the efficiency either needs to be higher, so you can cut fixtures, so you can cut wattage out of the room, or if it's the same, you need to add more wattage to that room so you're not saving any energy. So I think that's one of the reasons that LED has had such a hard time, is that it's been sold completely wrong. So you have lighting manufacturers that say, take down this 1,000-watt HPS fixture, replace it with my 640-watt LED, and your light's going to be the exact same. Well, unless your LED fixture is 40% more efficient, the science, it doesn't hold true. It's not right. So you've just taken out 40% of your light's correlated with yield, so now you have 40% less of your yield. So making sure that you're really understanding when you're evaluating the LEDs that you are comparing the efficiency of that fixture so you're not sacrificing the light levels in your room. So some of the different technologies that you'll see, the 1,000-watt metal halide, I haven't seen people growing with these in probably a year. They're still on the market, but it's just the cost of them versus some more efficient technologies is kind of passed through that. The 1,000-watt metal halides, they're not expensive. So the ROI on them, and depending on budget, makes them fairly attractive, and they do put out a lot of light. A lot of people have been switching to 315-watt ceramic metal halides because of the efficiency. So you need more of them, but you are saving, 40% energy over the metal halides. Single-ended HPS, again, not a lot of people left growing with that technology, especially on a big scale because of the efficiencies of a double-ended HPS when they're not really more expensive. And then LED, which is, I think, the future of lighting. And I said 3 years ago that I thought it would be 3 to 5 years before LEDs started to come on a big scale. I was in a facility last week in Canada that's putting in 6,000 LED fixtures into flower. So the time is here. Costs sometimes can still be prohibitive to do LED, but depending on the cost of power in your region, the financial payback is really starting to make sense. And also, when Bob comes and tells you about some of the rebates that are able to be achieved with LED lighting, again, depending on that cost of power, depending on what the rebates are, it's really financially starting to make sense. So I will leave you with 4 questions to ask when you're evaluating light fixtures. What's the efficiency of the fixture? If the manufacturer does not know what the efficiency is of their fixture, it's probably time to look at a different LED manufacturer. That's measured in micromoles per watt, and then verifying that the fixture is what they say it is. Are you targeting the right intensity for each stage of growth? Do you have that nice graduation from veg into flower, so you're not having shock going from the veg into flower? Is the spectrum correct? LEDs come in a lot of different spectrums. There's some manufacturers that have really figured it out. BIOS is one of them that's sponsoring this session. They figured out a great recipe for spectrum, and their fixture is pretty efficient with that spectrum. And then what is the cost of fixture measured in cost per U-mole? So making sure it fits into your budget, managing that ROI, and making sure that you're ready to make that leap from double-ended HPS into LEDs. So that's it for me.
Thank you, Kelly. Thank you, Shelley. So to close us out, Bob Gunn is going to be speaking with us about some rebate information that may be available to us. And brief commercial break here one more time is that directly following this session on the 4th floor, there will be a reception, and we invite you to join us there from 5:30 to 7. You could call it rebates, we call it free food, some hors d'oeuvres, close out the day. So please, Bob,
thank you, Ian.
Take it away.
Thank you all for staying to the bitter end. We saved the best for last. Energy utilities. I titled this slide deck, "Where are the Cannabis Utility Programs?" I'll try to answer that on slide 3, but then also give you a bit of a roadmap and a tutorial about how to navigate this world, because it's not very self-evident. My name is Bob Gunn. I'm from Seattle, Washington. I've been in the utility space for 10 years and working whole hog in cannabis for 2.5 now. I lend my utility rebate expertise to the cannabis industry in a consulting capacity, and also bringing financing to the table by bringing energy rebates and financing to growers to overcome that barrier to entry, which has been alluded to in other panels. Obviously, capital is constrained, but we're talking about utility money. So this is money that's on the table, and I want to help you get it. But first, utility rebates. They're a huge deal. According to ACEEE, that's American Center for Energy Efficient Economy, electric utilities spend over $6 billion every year on incentives, and those are going to residential, commercial, industrial, agricultural customers, and the consultants to help document all of these energy savings over a baseline, and we'll get into that. So $6 billion is a huge amount. I wrote $6 billion on top of a $20 billion market. We hear about cannabis being a $20 billion market. I don't know how you value that exactly. That's not my point. Is that of this $6 billion, we know that cannabis is about half the load growth in many places, like in Colorado. I imagine it's going to take up a ever-growing tranche of that $6 billion. So what if we could get $1 billion of utility dollars straight into your pockets? That's my personal goal. Just working with a handful of clients, I personally got $3.95 million in the last 2 years from utilities, approved projects that lands in growers' pockets, or to help them finance lights. So they were able to invest in really fancy lights. So how do you figure out where these utility rebates are? I did Google this afternoon in preparation for this. I Googled cannabis utility rebates, or energy efficiency rebates for cannabis, expecting to find a lot of utility programs. I found one, the Energy Trust of Oregon, And everything else you find is articles from The Guardian or the New York Times, articles about energy use in cannabis, saying rebates are available, but you can't find them. You won't find National Grid or Excel Energy, or, I mean, not to say they don't offer rebates, but it's difficult to find. So the answer of where are they is it's everywhere. There are 3,000 utilities in the country. It's difficult, A, to figure out who your utility is sometimes. You can look at your bill, that's a good hint. But within, most states have on average 60 different utilities. So once you figure out who your utility is, you could call them up and say, hey, I want to do a lighting upgrade. And they'll say, oh great, lighting, commercial lighting, we have a program for that. The call center will take you through the steps and you'll hit a dead end. And because LED horticultural lighting isn't lighting. And the fact that it's called lighting, I might even argue, is a disservice to getting incentives, because lighting programs are mature, they have standardized hours of operation, they're governed by codes, building codes, or Title 24 in California, that say you can only put this much lighting per square foot, and if you get more efficient than that, we'll give you a rebate accordingly. But cannabis lighting, any horticultural lighting is an industrial process, just as if you were milling lumber or using a welder. It's a process that is not governed by code. So that's why these projects are highly customized, and I'll try to articulate, without being too boring, some of the inputs and some of the outputs and the utility perspective, how they value their investment and why they're opening their checkbook to write you a big fat check. So let's see, if I hit this slide, there's no published baselines. Now, published baseline, that's what I'm talking about, code. I would say the baseline for a cannabis facility is 1,000 watts over a 4x4. Maybe you'd argue 600 watts in veg over a 4x4. That's what I'd say the baseline is. But you bring that to a utility person who's never seen a facility, they don't know that it's a baseline. They want to point to a study, a peer-reviewed study with statistical significance. That simply doesn't exist. So that's why there's kind of a bit of arm wrestling and partnering with the utility to show them what the reasonable baseline is, to say, like Shelley said, you're replacing this 1,000 watts with this 600 watts, and ensure that the utility's getting, or that you're not compromising efficiency, you're getting the same utility out of that project. So, standards. My last comment on this one, we heard a lot about standards earlier. There's standards for electrical safety and engineering safety, and the electrical engineers out there are putting forward standards about how you will measure lighting efficiency. Like Brian said, you can measure how many photons are coming out of a fixture. That's interesting. If we all had a standard way to measure that, we can compare apples to apples. But then how are those photons bouncing around in a reflector and coming down? And then how much of that is hitting your plants versus the aisleway versus the wall? We don't have a standard methodology for measuring that. Therefore, it's just kind of adding to the confusion when we're trying to compare this apples to apples. So those standards don't exist yet. That's why we try to work with professionals when talking to utility. Furthermore, qualified product lists are some things that utilities rely on heavily. They don't want to be on the hook for choosing winners and losers and saying this fixture looks good, this one doesn't. So for all other commercial lighting programs, which is probably half of utilities' portfolios, they have a qualified product list, and they say, well, for example, you've seen Energy Star. They say, we'll incent on Energy Star fixtures. Happens to be a Department of Energy program, and they're not dealing with horticulture yet, but they will. I give them a few years. But before we have horticultural lights on a qualified product list, it's on us to prove to them what we're doing. Okay, so estimated savings is different. I've made that point. A key term here is baseline. The utility wants to know, what are you installing, the efficient case, compared to a baseline. Now, if you have lights already, you can count them. I'm saying, I'm going to take out these 100 lights and put in these 100 lights. That's easy. But even if you don't have lights hanging, this is a misconception. If you don't have lights hanging, you can still get a rebate, and your baseline is what you would have reasonably otherwise installed. So if you have a greenhouse with no lights, you can still, and you're going to add 500 lights. Yes, you're adding load, but if you add the load more efficiently than you might have otherwise, that's the basis for the rebate. So that's why that's why the kilowatt installed in the baseline is negotiable. We have to convince the utility what's reasonable. What you're installing is pretty known. Annual runtime is generally the same in the baseline versus the efficient case. However, when we get into controls, especially when you have natural lighting in a greenhouse or mixed lighting, your efficient runtime might be fewer hours than your baseline runtime because your controls are responding to the natural sun resource. HVAC interaction is another one. Pretty much, well, you can, depending on how you model it, if you save 1,000 kilowatts worth of lighting, you're probably saving about another 250 kilowatts worth of air conditioning. And that's not how you would model it, but that's kind of the outcome. But you're reducing the air conditioning load. The best utility programs from a customer standpoint treat these programs as refrigerated spaces. Saying if you're reducing a heat source inside a refrigerator, the refrigerant will have to work less hard, the air conditioning works less hard. So hopefully your utility will give you credit for that on top of it and dollars to go along with that credit. Coincidence with peak gets towards what Brian was saying, demand response programs. Well, aside from the programs, we know that peaks are more expensive. Utilities will value savings that cut during the peak more than savings that happen at night. Luckily, these are strong, solid base loads. We know this room's going to be on 18 hours a day, 365 days a year, forever, and this room's going to be on 12 hours a day. So utilities can identify the peak kilowatt hours saved, and they might pay more for those than the off-peak kilowatt hours saved. And same thing for kilowatts. But yeah, peak versus off-peak, it depends on where you are. In Excel Energy pays only for demand, but you go on a Pueblo, and Black Hills Electric pays for energy only. A lot of places, Ohio, Pennsylvania, most of the East Coast, most of California pays for energy savings and demand. So they want that capacity savings as well as the long hours of operation. And costs. Finally, costs are not as simple as you would think. You know what the invoice is from your vendor. You're going to pay $100,000 for this, and the utility might pay you up to a certain cost cap. They might say, we'll pay up to 50% of the incremental cost. What that means is you have to back out what you would have otherwise spent. So if you would have otherwise spent $30,000 on some entry-level HPS, they'll give you half of that, 70. So again, this is all utility speak. There's no dictionary for knowing what they mean, but when they say cost, they mean incremental cost. So I'll give you a quick 2-slide example of some inputs and some outputs. Let's say you were going to swap out 100 HPS with 100 LEDs. And some of the inputs, you break it out by veg and flower. The hours per day are there. You'd multiply it by 365. The baseline wattage is the same. And this is a crude example because I have the price being the same for each one. But let's just say you go to 400 watts for veg, 600 for flower. Below that are your kilowatt and your kilowatt hours saved per year. So you're going to invest $130,000 in this project. What people want to know, and they're figuring out if they can buy these lights or how they're going to buy these lights, is what rebate are we going to get. So it doesn't matter if it's indoors versus outdoors. This is an indoor example. Here we show that it depends on where you live and the utility program. Here's First Energy in Ohio. That has the lowest one. Xcel Energy, paying just for the demand savings, is next up. PG&E in Oakland pays demand and energy savings. In Seattle, they're just giving it away, up to 70% of the project cost. So if you know anyone with T5s in Seattle, let's rip them out, because the utility, they have extremely generous programs and they're very successful, and it's a win-win. So I think finally, I'm going to close with, we haven't talked much about spectrum, and I'm not an engineer, so I'm not going to get into it. But I do want to show, the lighting spectrum, the power range is this 400 to 700 nanometer range, and there's only 2 curves on here. One is the yellow curve. That's essentially the human eye perception. Let's just call it lumens. Earlier I said if you tell a utility program you want lighting, they say, oh great, we have programs, they have to meet these certain lumens per watt efficacy. But if they ask you that, you're having the wrong conversation. You need to back up and turn the conversation towards custom horticultural application. The green curve here is not a peak load. That's a photosynthetic response to the lighting spectrum. So you can see if you have a lot of lumens, and it's right there in the middle, HPS has a lot of lumens. It scores pretty well on the lumens per watt, I believe. It doesn't mean it's going to be very good for plants. And different LEDs and ceramic metal halides, plasma, induction, they all have better spectrum, and I'm not here to pick winners at all, but suffice it to say, lumens are for humans, so don't talk about lumens. The existing tools that utilities have don't work, and trust me, they're working hard on getting standards and qualified product lists and working with groups like the Resource Innovation Institute to collect data and substantiate baselines and all these other claims. The need for standards is strong, and the application matters, meaning not just how you fill out the application, but where the lights go. It's not a prescriptive rebate. It can't be like a screw-in light bulb where they'll give you $2 down, because where you're going to put that light and how often, how long it's going to run matters a lot. So, and I think in closing, I say, well, thank you for hanging with us. Let's open it up for questions, Ian.
Yeah. So thank you to all three of our presenters, Brian, Shelley, and Bob. For those of you that do have questions, if you do have questions, there's a microphone here at either side. So we just ask that you ask your question into the microphone. I have a couple of questions that I'd like to get started with, and any of you can answer this first question. One of the things that you often hear with LEDs is that they have a much longer lifespan than traditional lighting, HPS, and metal halide. And I'm wondering if you can speak to the lifespan of traditional LEDs and where that might also provide or not some additional savings.
Yeah, so I'll start with that. So a big part about sustainability with LED is the fact that they will last for 50,000 hours, 70,000 hours, 100,000 hours. So when you take into account your calculations, you're planning on several years. The problem is that 50,000 hours is many, many, many years. So how does a manufacturer back up the claim that a light will last that long? What you should ask for when you're buying an LED light is an LM80 report. So this sort of gets back to standards, LM80. Any LED manufacturer should have this report if they're making a lifetime claim. So basically what we do, so at Thrive, we do this with our LEDs. You put them into an oven, and it's accelerated lifespan testing. And then every 1,000 hours, you take the LEDs out of the oven and you test how bright they are. And every 1,000 hours, the brightness goes down a little bit, because that's what an LED does. It dims very, very slowly over time. So based on this accelerated aging, and the Department of Energy publishes formulas on how you take this accelerated aging and figure out how long an LED will last. We almost always say L70 or L90. What that means, L70, the LED is dimmed to 70% its original output. Once it dims that far, we consider it end of life. It's time to replace it with something else. A lot of times in horticulture, we talk about L90, and that's the same thing, but dimmed down to 90%. So the way an LED manufacturer would do that is with this LM80 oven baking test.
What's the proper temperature to bake an LED light in the oven?
Yeah, actually, 3 temperatures. You do it at 55 degrees Celsius, 85 degrees Celsius, and 105 degrees Celsius. And then there's this fancy formula, because what we do with our fixtures, basically, you take this LM80 testing, then you turn on the light, and you measure what the actual temperature of the LED is in this light. So if you turn on, in the case of most of our fixtures, the LED is about 65 degrees. So we'll use the 55-degree oven and the 85-degree oven and extrapolate, and then we'll know that if you're installing it into a greenhouse at 35 degrees Celsius, here's how long the LED will last. If you're installing it indoors at 22 degrees Celsius, here's how long the fixture will last.
There's, with different LEDs as well, the LEDs definitely degrade, and some LED manufacturers have elected to put glass over the LEDs, so they're really easy to clean and take care of. Other manufacturers have no type of lens, and what can happen when they have no type of lens is they can get really dirty, and then that will also degrade the LED and shorten its lifespan significantly. So a lot of when you're deciding on which LED is look and see how long you think that maintenance is going to last, because even if the LEDs are rated for 75,000 hours and they're dirty and you can't clean them, you might be getting 60 to 70% of that light out of there, and the testing at the beginning is not going to show you that. So making sure that you're evaluating the construction of the fixture is also highly important.
And as far as hours, it's easy to get lost in big numbers like 50,000 hours. If you had a light on 12/12, 50,000 hours would be 11 and a half years. And that's, these are being rated to say they'll still be having 90% of their output after 11 or 12 years. And who knows what lighting is going to look like then. By comparison, a household incandescent bulb that we don't have much of anymore are rated for 800 hours. So it's far beyond, and well, I should say, and probably high pressure sodium bulbs, you're probably changing every, once to twice, once a year, probably, at least.
Double-ended is about 18 months of a lamp change out. So when you're calculating the payback of what these LED fixtures are, maintenance definitely comes into play along with the kilowatt hour cost, and then how much does that fixture cost? And then you calculate backwards to figure out what the ROI is. Most ROIs that I'm seeing, depending on the manufacturer, somewhere still between 3 and 8 years. A lot of them landing around 5-year payback, which is still a little bit long. But as demand increases for these LEDs, the thought is that the cost point will continue to drop. In 3 years, the cost point of LEDs has come down considerably. So as that cost point comes down, you're working with rebate professionals like Bob, your payback should be falling under 5 years, and then it really starts to make sense to me making the investment.
I'd say 5 years sounds conservative. I'm seeing a lot of them at 3 or 4 years without rebates, especially if you're paying more than 10 cents per kilowatt hour, which most of the country is. So 3 to 4 years without rebates in most cases, and with rebates, Seattle City Light, where I'm from, they cap it at half a year. They'll give you incentives until you get to a 0.5-year payback. At that point, they say, that's enough.
In Washington, every LED project where you're replacing T5s, half a year payback every single time, because they rebate 75% the cost of the lighting. Here in Colorado, there's a rebate on just about every LED project. It ranges, what we've seen, 15% on the low end, 35% on the high end. Although we've seen, that's for Excel territory. In other parts of Colorado, we've seen rebates as high as 65 or 70%. And in that case, payback is almost the wrong term, because the upfront cost is maybe less than other technologies.
When you're talking, clearly LED is coming a very long way very quickly, and one could liken it to perhaps what's gone on with microprocessors and computing. So if we were to take, I think it's called Moore's Law, and apply that to LED lighting, what do you feel is, with all the advances in technology, where are we as far as the opportunity to double the capacity or to double efficiency or to see new technologies coming forth in a short period of time?
Yeah, there actually is a law. It's Height's law. So you can Wikipedia
Pardon my
that.
ignorance. The lighting professionals are here, ladies and gentlemen.
It's basically, it's the same idea as Moore's Law, where instead of transistors doubling with LED, the amount of light that's emitted per watt and per dollar is increasing. It has been on a very steady slope since about the 60s. So we've been on the slope for a long time. LEDs originally were just indicator lights on calculators. They could just barely provide enough light to be an indicator. Then they've slowly become brighter. And really in the last 10 years, it's been on that curve where you get more light per watt, per dollar than other technologies. I think we're at the inflection point now, where 3 years ago, an 8-year payback, you're probably not going to buy LED in most installations. 8 years is too long. Now we're in this reasonable payback time frame. Sometimes as fast as 6 months, but usually 2 years, 3 years, depending on your cost of energy. Where are we on the curve? I think we have a doubling in the next 5 years, and then we get pretty close to that theoretical max. I think 10 years from now, we'll be at the maximum efficiency, but it will increase 10% per year for the next 5 years.
Okay. Shelley, you were talking about the switch, or some people using LEDs and some people using HPSs, and I'm wondering if you can speak to risks or challenges associated with making that jump and pulling one type of lighting and going into another in a facility.
Sure. So in veg, I've been seeing a lot of LED for years, and it working really well, rooting the plant really nicely. The flower switch is a little bit trickier, and I've seen some growers that have had a hard time converting. What I've seen work well is smaller testing, make sure that you have the temperature in the room correct. There's not nearly as much radiant heat coming off of an LED, which HPS heats up the plant a little bit better. Leaf temperatures remain a little bit higher. So if you're gonna make the jump, make sure you're testing it. But you know, like I said, there's people that are taking their whole huge facilities and putting all LED in it. Within about the last year, I've started to see more and more of it, which is really exciting. But there definitely are scary points that if you're not ready and you're familiar with HPS, that's what you've been growing with, the temperature, make sure you start small and have it sorted out before you go and build a gigantic facility with all LED, because there are very scary things that can happen if you're not ready for it.
Let me ask a follow-up to that to any of the three of you. Within a cultivation facility where one is trying to control all the elements environmentally, a lot of us don't have the luxury of setting up an entire room for a test. So what do you feel is an appropriate way, and how could somebody go about doing that and testing, because they want to make that jump, yet they're afraid that there's going to be some crossover from the lights that are adjacent, or they don't have a room that's small enough. How does somebody appropriately go about doing a test to determine if LED or whatever lighting may be best appropriate for them?
Yeah, I think that's a tricky question.
It is a tricky question.
If you're going to do an appropriate test and put it head to head, then you have to be able to monitor that environment and make sure that your temperatures are correct, that you're not, and it's a nightmare trying to sell lights also to people when they set up one light for the test, because one light as a test is not a significant test. You can have light bleed from your HPS that's coming in.
What is a significant test?
Well, from a lighting perspective, when you light a room, you get the uniformity and you get the compounding light levels. So if you're going to hang up 4 lights, with LED, it's more directional, so you can probably reach those light levels. With HPS, it's harder to get that. So with HPS, I would say a test needs to be probably at least 15, 20 lights on a bigger scale. With LED, you probably can get away with less because it's more directional. But then you have the temperature issues. I mean, your question's really hard.
That's why I'm here.
It is hard. We've seen different growers test different ways. In greenhouses, especially, this is more on the food side of the business where they might have 50 acres of greenhouses. They'll test 1% to 3% of their square footage, and they'll just retrofit a greenhouse maybe. And it's a big investment from a test perspective, but from their perspective, 1% to 3%. Indoor controlled environment, it's really hard to figure out what's statistical significance. Is it a 4x8 area? Is it an entire room? Is it half a room? I think just common sense there. What makes you feel comfortable with switching over?
Okay. Again, I'll invite if anybody from the audience has any questions. There's microphones on either side. I do have some additional questions though, if nobody else wants to ask any. Or you can just speak up loudly from the audience.
I mean, I think it's the holy grail, but the greenhouse in Canada, I mean, it's too new. But are there houses or buildings, whatever, indoor or outdoor, where you're seeing the yields with LEDs that the growers are seeing same yields with HPS?
Yes.
Did everybody hear that question?
And the reason being is, the question is, are you seeing yields with LEDs that are equaling HPS? And the answer is yes, and it's attributed back to making sure that you've got the correct light levels. So as long as you're not taking 40% of your intensity out of the room and you're targeting that same level of light, and in some cases, there's LEDs, some people would tell you that they're seeing higher quality come out of their rooms. But it has to be set up correctly, which is why LED has struggled for the last, since I've been in the industry. It sort of had a black eye because it was sold completely wrong. And it still is being sold wrong by a lot of manufacturers.
Yeah, I think Shelley's slide was spot on, where it all depends on how much light is hitting your plant. That's what it comes down to. So if an LED has the same efficiency as a high pressure sodium light, you're gonna have the same yield as a high pressure sodium light. If an LED has a lower efficiency, your yield's gonna be lower. So just look at the efficiency of the light, look at a lighting model, and within reason, you can't give thousands of micromoles to a plant. But if you're targeting 600 micromoles for flower or 800 micromoles for flower, your yield will be roughly the same, regardless if you're getting that micromole from the sun or from a high pressure sodium or from an LED. So with an LED, sure, you can get higher yield if the efficiency is higher.
Okay, so then, very good question, sorry. What equal yield with savings from an LED? And if so, is it 10% savings? Is there no savings?
No, so there's savings. So it's back to that efficiency number. So if you have a double-ended HPS that's 1.8, 1.9 roughly, and you're now coming to, and the full spectrum LEDs on the market right now are roughly 2.2 to 2.3. The red and blue ones, which are more targeted towards greenhouse, just that supplemental source, you don't need as much of the spectrum. That's 20 to 40% efficiency in your light source that directly attributes right to your energy bill with that same light level. But if you have an LED that's less efficient, and there's a lot of them that are less efficient than double-ended HPS, then there is no efficiency, and you might actually be going backwards.
Well, and you're talking about electrical savings. So yeah, I'd say 30 to 50% savings is what you can expect because you have the lower energy bill. But you touched on this, but kind of went past it. That usually LED rooms you can run about 4 degrees warmer, so your air conditioning that much less. So that's another big deal. And in greenhouses, controls work so much better with LEDs, and I think that's still an emerging technology, proper controls. But that's something that most LED companies can, work with plug-and-play materials where then you can cut your hours in half, so you're not getting more DLI, more daily light integral than you want for your plants.
So I would define yield in 2 ways, say grams per watt or grams per square foot. So it all depends on what you're trying to optimize there. Grams per watt, easy, yes. You can have higher yield, no problem. Grams per square foot, I think that's where LED historically has oversold itself, saying that you will have the same yield as a double-ended high-pressure sodium with 40% less energy. It wasn't going to happen. It's still not going to happen today. I think a 40% energy drop, it doesn't make sense if a double-ended high-pressure sodium, 1.7 or 1.8 micromoles per joule, and a full-spectrum LED is 2.2 micromoles per joule. You can do the math. You can't cut your energy bill by 40% there. But if you're talking about targeting the exact same PPFD, maybe slightly higher PPFD, I think you can get better grams per square foot and better grams per watt.
One of the things that we were talking about earlier was the cost per kilowatt, and I'm wondering if there is an area or a price that becomes a break-even point for investing in LEDs.
Do you mean the cost that you're paying for energy?
Yes.
I think it pencils at any rate. The lowest you'll see an industrial rate is probably 5 cents, maybe 4 somewhere in the country for an industrial big commercial customer. That might, your payback might be 10 or 15 years at that point. But you guys might have researched it more carefully. When you get above 10, it just pays off so darn quickly. And demand savings are often overlooked. Your demand is if you spike for 1 minute, you're going to pay to have that bandwidth open to you for the next 2 months or the next 12 months, and you'll pay for that bill 6 or 12 times over. So I don't have an answer there. You guys might know better.
I think that it's Depending on that cost, like he said, anything over 10. A year ago, I was saying it looked really great when you got to 15 cents. It's probably even lower than that now because some of the cost of these LEDs is continuing to come down a little bit. Somewhere between 12 and 14 would probably be a really nice sweet spot and if it's higher than that. I mean, we had a customer in Hawaii that installed them and their payback was, for the whole facility was flowering, the whole thing. They were in the high 20s, low 30s, and their payback was less than a year. So, and in places like that, in some areas of Canada, some areas in the Northeast, the financial piece of it makes complete sense to go to LED. And then you have to measure if you're ready for that, and you're managing the temperature correctly, and all of those other sources then come into play in those decisions.
The other big thing to look at is time of use. You see a lot of LEDs in veg because they're on 18 to 24 hours per day. So when you're selling an energy efficiency technology, it only matters if the lights are on. So for flower, the lights are usually on 12 hours per day. So it's more challenging to have a payback. When you're talking about greenhouse supplemental, again, it's more challenging because the lights won't be on in the summer, maybe at all. Maybe it's only 6 months out of the year. So it's cost of energy and then how often are the lights on.
Okay. Bob, I think you said that $3.8 million in rebates, is that what you suggested? That you personally have saved customers?
Yeah,
about
a little
3.8 million? Can you?
Who's counting?
3.972 million. What's the average rebate, if there is one, or if you could perhaps quantify for us, what is the average rebate that a cultivator is saving when you're working with them?
No, I can quantify it. It averages about $60,000. And oftentimes, because they can afford to do about $100,000 or $150,000 worth of lighting, they might want to do $500,000, but they can, at least in Washington and Oregon and Colorado where I'm working most, California thus far, I have a lot of interest down there, but they're getting ready for California. People are building out slowly as their capital allows. So 60,000 is typical as a rebate. The biggest one was $713,000, and that was for $850,000 worth of fixtures. We talk about a slam dunk. That was for a greenhouse, all veg. Actually, no, that's not true. No, it wasn't all veg, but it was definitely a huge greenhouse.
So you paid just over $100,000 for almost $1 million worth of lighting.
Exactly.
It's pretty phenomenal.
Yeah, and then and oftentimes on these commercial rebates, utilities won't even look at them if it's not at least X kilowatt hours savings. Some utilities say the rebate has to be at least $3,000 or $10,000 to put an engineer on it.
Pretty significant savings.
Big savings.
Can any of you speak to, when you're dealing, I know you touched on it briefly in the presentation, but perhaps in more detail, when you're dealing with LED lighting, there's obviously a lower heat load as a result of that. So I'm wondering if any or all of you can speak as to how lighting affects HVAC. Savings standpoint, energy standpoint, overall standpoint, output in terms of production, all of that's on the table.
So a watt is a watt to cool. Doesn't matter if it's HPS or LED, and the calculation is 3.41 BTUs per watt. So you take your total wattage in the room, times it out, and then you send it to your engineers to cool it. So if you're taking out, 30% of LED, then you have that much HVAC that you also have to put in it, and there's engineers that calculate that all day. There's other heat sources that you have to take into consideration in the room, so it's not completely accurate. The lights for sure put off that much. And then the engineers take it from there. But the thing with LEDs too is that when all of the LEDs shut off, well, with any of the lights, then sometimes you have to add a little bit of heat back into the room because it can cause issues with that temperature differential.
Well, and upfront sizing. If you know if you know you're going to go LED instead of an HID, you might be able to get away with 150 tons of cooling instead of 200 tons of cooling. So that right there might save you $50,000. Or you can ask the utility for 2,000 amps of service instead of 3,000 amps. Or a lot of people, I've had some growers who shut a couple HID rooms off in the summertime. They just can't keep up with the air conditioning. And they come to me saying, hey, what options are available? I'm down a room and that's $100,000 I'm not going to make this summer. And they only have 600 amps of service, so we can run some numbers and just get more utility out of that facility because of those physical air conditioning constraints. But yeah, capital costs up front add up.
Yeah, I would just like to second what Shelley was saying, that there's nothing magical about LED. A watt of LED needs to be cooled the same way that a watt of high pressure sodium needs to be cooled. So be careful with some claims that an LED will cut your HVAC in half or to a third, because you still need to cool every connected watt. Now, LED can be more efficient, so if it's 20% more efficient, 20% less HVAC, that's totally fair. But be careful, size 3.4 BTUs for every connected watt.
Plus a little bit more.
Anybody from the audience? And if you would, please use a microphone, because as I understand, we're recording and we can't hear, the cameras can't pick up the questions from the crowd.
Can you hear me?
Yes.
All right. My name is Michael. I'm from Solitube International. We make tubular gate lighting devices to bring sunlight indoors. Had a lot of interest from growers following Dr. Jonathan Cachet's research on the sun-grown indoor method. This question is mostly for Bob. Do you see most of the 3,000 utility companies out there in the country being able to offer incentives on daylighting equipment, even though it's not actually providing an electric light source, just reducing it?
Speaking for myself, yes, I do. And it gets back to that question of baseline. And I've seen these solar tubes, they're really cool. You have a solar tube and an LED. So you still have, let's say a 600 watt LED installed, but this big $2,000 controller essentially makes it, instead of operating 4,000 hours a year, it operates 2,000 hours a year, much like a greenhouse. So I think utilities will be able to understand that, but it's on us to document what's normal, what they would have otherwise installed. But yeah, there's no programs for that right now. It's a lot of custom work. You have to make your case, but I don't see any reason why they should say no to that.
It's definitely yes. In general lighting, this sort of skylights or day lighting, it exists. It works easier for retrofit than new construction. And I would encourage you to look at it, because the most efficient light is one that's off. If you can use the sun, that's nice to have. It's challenging to pipe in enough sun from outdoors. It's challenging in a greenhouse. From Shelley's slide, in the winter, you might only get 10 moles of light per day. An average greenhouse, only 65% of that goes through. Through a solar tube, it's maybe even less. It's worth looking at because they're free photons and you can get rebates on them, but you have to make sure that the numbers work out well.
There's a company out of Boulder, Colorado, I think, that's doing something similar. Their name has escaped me at the moment, but I know from hearing them pitch several times that they have received several $1 million from, I think, the Department of Labor or the Department of Energy, and was one of the first companies to get federal funding for this lighting that they plan to use for cultivating cannabis. It's been interesting from an investor standpoint to watch all of the different lighting that has come into the arena, and I have yet, and perhaps if there is one that is in a licensed cultivation facility, but I have yet to see it in any licensed cultivation facilities, at least in Colorado. Are you aware of that existing in any?
Some in design right now in Colorado, actually.
Got it. Yeah, it's fascinating, especially where we have 300 plus days of sunshine a year, and the opportunity to take that straight from outside and pipe it indoors.
Sir, how much light do you think from the solar tube you actually bring into the room?
It depends on the model you're looking at.
Do you mind using the microphone, please, just for the purpose of recording?
Welcome to the panel.
Yes, thank you.
Thank you. It really depends on the model and, of course, where you are in the country. Your available sunlight is going to make a big difference. But we have optics that collect low-angle sunlight, so even in a real northern climate, you know, as long as you have clear sky conditions, you can still get a lot of available sunlight. In regard to, you know, how much light you're bringing in, could be 40,000 lumens for our larger units, so pretty significant. But that's full spectrum sunlight. I mean, it's different than what you're getting with LEDs or HPS. I mean, you're just getting a sliver of light spectrum. This is, you know, this is actual sunlight. So, but we do filter out the infrared spectrum, so we're not bringing in the majority of the heat. But yeah, you get pretty significant light. I would say probably equivalent to like a 650 watt metal halide, something like that, for like our larger units.
Ian, the company in Boulder is Sunderland.
Sunderland, that's not the one that I'm thinking of, but there is,
Or are you thinking about the fiber optic one?
perhaps, yes, yeah. Jim Kelly knows a lot about lighting as well, as well as recycling and some energy rebates. So he's a great person to speak with as well. Do any of the three of you have any closing thoughts specifically that you'd like to say before we get out of here?
Don't leave the money on the table.
So obviously, we need to become more sustainable as an industry, and a lot of this technology is already out there. From lighting design to rebates to HVAC design, use it, read it, look at it, and I think there's tremendous opportunity right now to save energy if we just start applying some of these technologies.
Cool. So once again, Bob Gunn all the way on the end of the stage from Synergy LLC. Shelley Peterson, the Vice President of Lighting Technology at Urban Grow. Brian Bennett, CEO of Thrive Agritech. My name is Ian Sieb from Denver Relief Consulting. Please join us on...